Welcome back. In the last lesson, we introduced a new data structure called a linked list. In this lesson, we'll visualize a linked list as a set of nodes and see how operations are carried out on a linked list. So in this lesson, we'll visualize a single node and then see how nodes are joined together to create a linked list. And using this visualization, we'll see what happens when we append, insert, or delete nodes from the list. So a linked list is made of nodes. A single linked list node stores two values, some data and a pointer. We can visualize it as a double box like this. Of course, there's not really boxes like this inside the computer. This is just a way of visualizing it. We can also visualize the nodes being joined together. The pointer of one node is the address of the next node. We often show this as arrows. Of course, there aren't really arrows inside the computer. The pointer is a numerical data value, which is the numbered location of the next value. The start of a linked list is called a header. The header has a pointer but no data. To find the rest of the data in the linked list, the computer has to follow the pointers, starting at the header. Of course, there can be many values in the list. At the end of the list, there is a final node that points to nothing. We might write this as null, or in Python we would write it as none, the word none, which is a Python keyword. Either will be fine in the exam. So let's recap what we've seen so far. A linked list is made of nodes. Each node has got a data value and a pointer. The pointers join the nodes together. The header is the pointer to the first node, and the final node points to nothing, and that's how we know it's the end of the list. Now let's look at how we would carry out simple operations on a linked list. For example, here's a very short linked list. It's only got one value in it, the data value A. Supposing I wanted to append data to this list. Remember, append means add at the end. First of all, we would create a node with the new value in it. In this example, I'm going to add the value B to my list. Then I add a pointer. I replace the old null pointer at the end of my list with a pointer that points to my new data. B has now been added to the linked list. So my linked list, if I traversed it, would go A, B. B is the final item in the list, and it has the null pointer. Now supposing I wanted to insert a node into the list. Let's say I wanted to insert the value Z in between A and B. So I'm not appending, I'm not adding at the end, I'm inserting halfway through the list. First, I would create a node with the value in it. It's not part of my list yet. I change the pointers so that the first node A is pointing to Z and the node Z is pointing to B. Now if I traversed the list, it would go A, Z, B. Z has been inserted into the list. Let's look at that again. The first thing I have to do is hook the new node onto B. If I don't do that, then all the remainder of the list will be lost. Remember, the computer only knows where values are by following the pointers. So the first thing I've got to do is make sure that my new node is joined on to the remainder of the list. And only when that's been done can I change the pointer at A to point to Z. If I did it the other way round, I would lose the end of the list. So that's very important when we come on to programming a node, a linked list. Similarly, let's decide to delete a node. Now I'm going to delete A from the list, but the same thing will apply whichever value I want to delete. All I have to do is change the pointers. The computer will now skip over A. It will start at the header and go straight to Z. I don't have to delete that node from the computer's memory. I don't have to wipe it out or overwrite it. I don't even have to change the pointer. I just bypass it. It's like we built a road round a town and all the cars just drive round the town and don't go through it. So A is effectively deleted from our list just by changing the pointers. And this is how we delete items from a linked list. So to recap, if we want to append data to a list, we make a new node and then change the final pointer of the list to point to the new node. The node is now added to the end of the list. If we want to insert a value halfway through a list, we have to make a new node and then we have to change 2 pointers so that the new node is integrated into the list and nothing is lost. And finally, if we want to delete a node from the list, we don't have to wipe it from the computer's memory. We just change the pointers so that the computer will skip over the node. There are some advantages and disadvantages to using a linked list. A linked list is dynamic and flexible. You can make changes, add and take away nodes at any position in the list. And if you've got any spare space in memory, you can put nodes there and just link to them. Editing and deleting from the list is quite easy. You only need to change the pointers. So a linked list is a great data structure in many ways. It does have one disadvantage. Because it works using pointers, the computer has to follow the chain of pointers every time you want to do any actions, and so it can be a bit slow. So in this lesson, you should have come to understand what a node is in a linked list and how we make a list by joining nodes together with pointers. And you should have some idea of what happens when we append, insert or delete nodes from a linked list. I'm leaving you with an activity. Using the visualization method that I've shown you in this lesson, draw a linked list with the values A, B, C. Show each node as a value plus a pointer. And now show what happens when you append D to the list, insert X after A and delete C from the list. Do the actions in that order and show how the pointers change and how new values are added or taken away. As pointers, you can just use arrows for now if you like, as I've done in this lesson. Okay, so have a go at that. In the next lesson, I'll look at how we can also show linked lists using a 2D array. So I'll see you then. Bye for now.